Most of the chemical reactions are accelerated by an increase in the temperature. For example, in the decomposition of N2O5, which is dinitrogen pentoxide, the time taken for half of the original amount of material to decompose, which is also known as the half-life, is 12 minutes at 50 degrees Celsius. It is 5 hours at a temperature of 25 degrees Celsius, and it is 10 days at a temperature of 0 degrees Celsius. We notice here that as we increase the temperature, the rate of the chemical reaction also increases, or as the temperature decreases from 50 to 25 to 0 degrees Celsius, we see that it takes much longer time for half of the material to decompose. It has been found experimentally that for a chemical reaction with a rise in temperature by 10 degrees Celsius, the rate constant is nearly doubled. The temperature dependence of the rate of a chemical reaction has been accurately explained by the Arrhenius equation. The Arrhenius equation was first proposed by a Dutch chemist, J. H. van 't Hoff, but Swedish chemist Arrhenius provided its physical justification and interpretation. The Arrhenius equation is K, which is the rate constant for the chemical reaction at temperature T, equals A multiplied by E raised to minus EA divided by RT. In the Arrhenius equation here, K is the rate constant of the chemical reaction at that particular temperature T. T is the temperature in units Kelvin. A is the Arrhenius factor, which is also known as frequency factor or the pre-exponential factor. The Arrhenius factor A is a constant specific to a particular reaction. In the equation, R is the gas constant and EA is the activation energy, which is measured in the units joules per mole. Let us understand activation energy by taking a simple illustration. Let us say hydrogen gas reacts with iodine gas to form hydrogen iodide. That is, the reaction is H2 plus I2 reacts to form the product 2HI. Now, according to Arrhenius, this reaction can take place only when a molecule of hydrogen, which is H2, and a molecule of iodine, which is I2, collide to form an unstable intermediate. Now, in this case, the molecule of hydrogen and the molecule of iodine collide to form the unstable intermediate H2I2. This unstable intermediate exists for a very short period of time, and then this breaks up to form two molecules of hydrogen iodide. That is, the unstable intermediate H2I2 forms 2HI. The energy required to form this unstable intermediate, called the activated complex denoted as point C on the graph shown alongside, is known as the activation energy, which is denoted by the letter capital E with A as a subscript. In the graph shown, energy of the reaction is plotted with the reaction coordinate, that is time. At point A, H2 and I2 are yet to react. At point C, the activated complex has formed, and point B is where the final products, that is 2HI, are formed. The difference in the potential energy between point A and point C, which is the point where the activated complex, that is the unstable intermediate H2I2 forms, is known as the activation energy. Some energy is released when the complex decomposes to form products. So the final heat of the reaction depends on the nature of the reactants and the products. In the previous section, we understood the statement of the Arrhenius equation, which is K, which is the rate constant for the chemical reaction at a temperature T, equals A, which is the Arrhenius factor, multiplied by E raised to minus EA, which is the activation energy, divided by RT, where R is the gas constant and T is the temperature at which the reaction is taking place. Let us now understand the graphical representation of this Arrhenius equation. To plot a graph, we will have on the x-axis 1 divided by the temperature 1 by T, and on the y-axis natural log of the rate constant, which is ln K. Then the graphical representation of the Arrhenius equation, K equals A e raised to minus EA by RT, is found to be a straight line with a negative slope, and the slope of which is equal to minus EA by R, that is minus of the activation energy for the reaction divided by the gas constant. The y-intercept is ln A, that is the point where the straight line crosses the y-axis is ln A, that is natural log of the Arrhenius factor. Let us now understand how the rate of a reaction differs at two different temperatures. To compare the rate of a reaction at two different temperatures, let's say T1 and T2, let us say we have the rates of the reaction or the rate constants of the reactions as K1 and K2. That is, at time T1, the rate constant for the reaction is K1. At time T2, the rate constant for the reaction is K2. Now, using Arrhenius equation, we can find the expression for the rate constants at the time T1 and T2. That is, we can find the expressions for K1 and K2. So, at the temperature T1, we can write that rate constant at that temperature, which is K1, equals to A e raised to minus EA by RT1. Here, T1 is the temperature. Similarly, at temperature T2, we can say, using the Arrhenius equation, that the rate constant at T2 is K2, which is equal to A e raised to minus EA divided by RT2. Here, T2 is the temperature in Kelvin. Let us divide the second equation by the first equation. When we divide the second equation by the first equation, we get on the left hand side of the equation K2 divided by K1, and on the right hand side of the equation we have E raised to minus EA by R brackets 1 divided by T2 minus 1 divided by T1 bracket close. Let us now apply log on both sides of this equation. When we apply log on the left hand side of the equation, we get log of K2 by K1, that is log of rate constant at temperature T2 divided by the rate constant at temperature T1 equals minus EA by R multiplied by brackets 1 by T2 minus 1 by T1 log of E. Let us convert the log on the right hand side of the equation to natural log. To do that, we need to divide by 2.303. When we do that, we get on the left hand side of the equation log of K2 by K1 equals EA divided by 2.303 R multiplied by brackets 1 by T1 minus 1 by T2. This equation gives us a comparison. Let us solve a few questions based on the Arrhenius equation. The question is, the rate constants of a reaction at a temperature of 500 Kelvin and 700 Kelvin are 0.02 per second and 0.07 per second, respectively. Calculate the values of EA, which is the activation energy, and A, which is the Arrhenius constant. Now notice the values that are given to us in the question. We've been given the rate constant K1 at temperature T1, that is the rate constant 0.02, which is at the temperature of 500 Kelvin. Hence we can say that the value of K1, which is the rate constant at temperature T1, is equal to 0.02 per second. Similarly, the value of T1, which is the temperature, is 500 Kelvin. We've also been given that at 700 Kelvin, the value of the rate constant of the reaction is equal to 0.07 per seconds. Hence, we can say that the value of K2, which is a rate constant at temperature T2, is equal to 0.07 per seconds. And the value of T2, which is the temperature, is 700 Kelvin. We are required to find the values of EA and A. That is, we need to find activation energy, which is EA, and A, which is the Arrhenius constant. Now here we have been given the two rate constants at two different temperatures. So we can use the formula or the equation log of K2 by K1 equals EA by 2.303 R brackets 1 by T1 minus 1 by T2. Now here when we substitute the values of K1, which is equal to 0.02 per second, K2, which is equal to 0.07 per second, T1, which is 500 Kelvin, and T2, which is 700 Kelvin, we get log of 0.07 divided by 0.02 on the left hand side of the equation equals EA, which is the activation energy, divided by 2.303 multiplied by 8.314, which is the gas constant, that's the value of R, multiplied by 1 by 700 minus 1 by 500. Let us simplify this equation. When we find the log of 0.07 by 0.02, which will be log of 7 by 2, on the left hand side of the equation, this is equal to 0.544, which is equal to EA multiplied by 5.714 multiplied by 10 raised to minus 4 by 19.5. Now from this equation, making EA as a subject, we get the value of activation energy EA equal to 18,230.8 joules. So hence the activation energy for the reaction is 18,230.8 joules. In the question, we are also required to find the value of A, which is the Arrhenius factor or the Arrhenius constant. To find the value of A, we'll again use the Arrhenius equation, which is K equals A multiplied by E raised to minus EA divided by RT, and substitute the value of the rate constant K and the temperature T for any one of the temperatures which are given to us here. When we do that, we can find the value of A by making A as a subject. Using this formula, we find that the value of A is 1.61. Hence, for this reaction, the activation energy is 18,230.8 joules and the value of A is 1.61. Let us solve another question on the Arrhenius equation. The question is, the first order rate constant for the decomposition of ethyl iodide, which is C2H5I, is given by the reaction C2H5I in gaseous form forms C2H4, which is ethane, plus Hi, which is hydrogen iodide in gaseous form, at a temperature of 600 Kelvin is equal to 1.60 multiplied by 10 raised to minus 5 per second. It's given that the energy of activation is 209 kilojoules per mole. Calculate the rate constant of the reaction at a temperature of 700 Kelvin. Let us understand the information given in the question. It's given that at a temperature of 600 Kelvin, the rate constant is 1.6 into 10 raised to minus 5 per second. We need to find the value of the rate constant at another temperature, which is 700 Kelvin. Therefore, as we are comparing two rate constants at two different temperatures, we'll use the formula log of K2 by K1 equals EA by 2.303 R multiplied by brackets 1 upon T1 minus 1 upon T2. Let us now substitute the known values. Here, the value of T1, which is the temperature, is 600 Kelvin. The value of K1, that is the value of rate constant at 600 Kelvin, will be 1.6 into 10 raised to minus 5. The value of T2 is 700 Kelvin. The value of EA, which is the activation energy, is equal to 209 kilojoules per mole. Converting to SI units, we can write this as 209,000 joules per mole. The value of R, which is a gas constant, is 8.314. When we substitute these known values in the above equation, we get on the left hand side of the equation log of K2 by 1.6 multiplied by 10 raised to minus 5 equals 2,09,000, which is the activation energy, divided by 2.303 multiplied by 8.314, which is the gas constant, multiplied by brackets 1 upon 600 minus 1 upon 700. Now here we need to solve this equation to find the value of K2. On the left hand side of the equation, we can write log of K2 minus log of 1.6 multiplied by 10 raised to minus 5 equals 2,09,000 divided by 2.303 multiplied by 8.314 multiplied by brackets 1 upon 600 minus 1 upon 700. Transposing log of 1.6 into 10 raised to minus 5 from the left hand side of the equation to the right hand side of the equation, we get log of K2 equals log of 1.6 into 10 raised to minus 5 plus 2,09,000 divided by 2.303 multiplied by 8.314 multiplied by brackets 1 upon 600 minus 1 upon 700. Now on the right hand side of the equation, the value of log of 1.6 into 10 raised to minus 5 is minus 4.796. Also evaluating the value of the second term on the right hand side of the equation, it's equal to 2.599. Hence we can write log of K2 equals minus 4.796 plus 2.599, which is equal to minus 2.197. On taking the antilog on both sides, we get the value of K2 equal to antilog of minus 2.197, which is equal to 6.36 into 10 raised to minus 3 per second. Assignment for today's session is given below. Do ensure you complete your assignment before we start with our next session.